very happy that you give me the opportunity to talk about some of the work we're doing since 5-6 years around the development of cardiac biosensors using gFET technology. As you might know, cardiovascular diseases are one of the leading causes still of deaths worldwide. We have around 80 million per year. It's around 31%. If you're actually out of breath, you might have a chance to go to hospitals and then you get some more sophisticated analysis using electrocardiograms or chest trays. But actually, if you will get to emergency rooms or to urgencies, the first thing will actually happen to you will get the cardiogram. You see here, these cardiograms actually 70% of times people are sent home and then actually later they get a heart attack at home. That means most of the times next to these cardiograms, you will get blood tests based off ELISAs. Now, I guess we all know ELISAs, we all know blood tests, we know that they're invasive. They take some time in hospital that you can get some results and they're not continuous and not rather costly. So I want to show you different technologies development we did around these cardiac biomarkers to probably find alternatives to this blood-based ELISA tests. But before actually I want to talk about the test itself, let's look which type of biomarkers actually we would be interested in sensing. If you look at the recommendations of the European Society of Cardiology, what they actually say is there should be a serial troponin testing, which is actually recommended when the patient comes into hospital and he says he has more than 6 hours an onset of a breath problem. This is in particular interesting if you look at this biomarker diagram here on the left. So when you actually look at troponin, you see that only after around 3-6 hours, troponin level actually starts to rise, which is an indication of some cardiovascular diseases. So that's this recommendation that actually serial troponin testing is required. Serial troponin testing means several times of blood drawing. Now let's put some numbers into this whole story. For somebody who's healthy, we have a CGNI level of less than 10 picogram per milliliters. So to actually have a test which can distinguish between a healthy and a non-healthy person, this is sort of the limit of detection you have to target. Now you have to consider that when you actually have AMI, that means acute myocardial infarction, you have a CGI levels 3 times the order of magnitude higher than actually this low level. So which type of sensors are out there? Well, there's the very famous, extremely sensitive eSTAT cartridge-based CGNI test for blood and for plasma, which has a limit of detection around 20 minutes. Widely used in clinics, you need around 17 milliliter on this. And it actually has a turnaround time, mostly about 98% in 60 minutes, which is mostly required and needed in hospital setting. So you might ask me, well, there's already something out there. Why actually we are interested in alternatives? Well, it is this blood drawing and this not possibility probably of continuously sensing cardiac troponin levels, which made us interested in finding alternatives. And now you are the right people to know that wearable point of care devices are sort of the future of sensing nowadays with a beautiful review, and there are several other reviews articles on this method just coming out. So I'm not going to talk about all of this, but I will focus on something which is around face mask breathing. And this idea actually started, like you can imagine, with the COVID crisis, where we engineered face masks to collect not breath, but actually breath condensate. So what we take, actually, we take commercial masks and we have like a Teflon inside with some materials which can be strongly cooled. That means if you breathe on it, you will have condensation on it. And the beauty of this exhaled breath condensate, as you call it, it's not only containing small volatile molecules like acetone or glucose, but it actually can contain droplets. And in these droplets, you will find proteins inside. So this is actually, we started to validate on this COVID virus. So at this time actually was known when you're coughing, you will cough around 10 to the 3 viral particles per milliliter out. if you compare this to sneezing, you get an Oerknoffen magnitude high, around 10 to the 4th viral particles out. So what we actually did, we let people breathe for 5 minutes in this cold masks, and then we evaluated by PCR testing the amount of particles which you will actually have in this condensate press. And you see, but depending on the infection level, you have something between 10 to the 3, 10 to 5 viral particle per milliliters, which can give you already an idea which kind of sensitivity you would use for this type of matrix to do a sensor. I'm not going to talk about COVID, but exactly at this time, we were working with some cardiologists at the CHU here in Lille, and we said, why not putting these masks on as well on people who have cardiac problems, who are before or after getting a viral cardiac surgery. And to our big surprise was when we let these people breathe onto the masks. So you see here on this graph stage A, B, C, D, that means it's the severity of the person who are having a cardiovascular problem. And we measured here actually the pro and TPMP level. And you see that as more severe the illness is, more severe the plasma level of this biomarker is increasing. And the EBC level seems to follow almost the same trend, with actually no at all biomarker present in healthy people, but then increasingly involved. So this made us thinking, could we use engineered masks for helping overcome blood drawing and therefore very rapidly diagnose heart failures or cardiovascular issues? So going away a little bit for the mask, now what I wanted to say, the sensor we developed is a graphene-based field effect transistors because it's miniaturization possibility, its portability, and the possibility on getting these nanomaterials inside. As in field effect transistor, we measure surface charge. It's sort of the ideal material actually to do this type of things because it's chemical inert and it's very sensitive. So how do we do these sensors? It can be either on glass or in flexible material like polyethylene. We have interdigitated electrodes, and actually we transfer this monolayer graphene on it. That we managed to do it. You see this on these SEM images, quite nice roughness. You see that the D band is very low. That means it's quite pure monolayer graphene on it. When we did the first IV curves, we were extremely disappointed because if you look at the slope and if you look at the Hall and electron mobility, they're extremely low values. You know, nothing compared what you have with graphene. We looked at ways if there are holes inside or nothing. So the first thing we said is if we would do surface modification, could we improve this charge mobility? And this is actually what you see here in this transparency. So what we did an electrochemical based diazonium chemistry using this what we call TIPS molecule. So it's a diazonium salt with an extremely bulky Si group. This is actually important because during this reduction, you therefore will form a carbon-carbon bond on this graphene, but you will limit it to a monolayer. So you can actually not polymerization off, and this is very important for a good field effect transistor. And if you do this actually cycling one time, you see here on the right-hand side, the IV curves, you extremely increase now the charge mobility. So from 700, we get now to around 1,700 centimeters square volts squared per second. So we wanted to see actually how many defects would get onto these surface chemistry approaches, because forcingly you convert sp2 carbon into an sp3 carbon with this type of approach. And you can actually use Raman spectroscopy and the ratio between the IT and the IG level to get an idea of the type of effect size. So the density of defects we actually have is around 10 to the 12 centimeter minus 2. And if you estimate the maximal saturation, it's actually 10 to the 15th. So we are definitely having defects on it, but we are not saturated in it, and that's probably the reasons why I have very nice charge transfer curves. You can also look at the change of the width of the 2D and the G bands, and you actually see a shift to higher wavelengths, and this actually indicates a B-doping effect. So you wonder where we are probably with the sensors. So you can actually deprotect these tips, and you end up with triple bonds, and then on triple bonds we can use classical click chemistry on it. And we used in this case as a model ferrocene N3 unit, because like this we can quantify as well the amount of ligands attached to the surface. So the XPS shows the iron peaks, but from the integration of the cyclovoltammogram, you can actually know that you have 10 to the 10th mole per centimeter square, which is around 86%. Now for sensor, which is important as well, is to look at the charge transfer characteristic, but you see actually we only shift the Dirac point, we keep the charge mobility constant even after surface modification. Now one issue always in this liquid gated gFET field effectors is the Debye length screening. That means the Debye length is actually indirectly proportional to the 1/I, which is the ionic strength. That means as higher the ionic strength, as lower this Debye length, and this is a huge problem for biological sensing because we have like Debye lengths of around 1 nanometers. So in principle, how should the sensor work on this? So one reason, one possibility to overcome this is using like semi-permeable membranes like polyethylene glycol. And this is what you actually see here when we have one of our graphene field effect transistors. And we only put a bioreceptor, I will come later to this, which is an aptamer on it, or a mixture between polyethylene glycol and aptamer. With the aptamer already at the PBS solution of 0.0x, actually you are completely UC signal. But with the PEG on it, you can actually measure current changes up to 1 ppx. So you're getting very nicely into the biological window. The other important thing is not only the semi-permanent membrane, but also the bioreceptor for itself. If we consider a simple bioreceptor, which is a size around 40 nanometers, we do all agree that probably the binding will be outside of the binding pockets of this antibody. So there is a tendency now in using engineered antibodies, either antibody fragments up to nanobodies or smaller fragments to put on this type of interfaces to be in the conditions of overcoming this Debye leaf screening. I'm not going to talk nanobodies because this is work just going on. I will talk more about aptamers, as I said, and in particular, I want to show you here a comparison between two aptamers. A DNA aptamer, mostly used in the literature, but charged, and therefore could have an effect on the graphene field effect transistor reads out. And another aptamer called a PNA aptamer, which is not charged and therefore should have a lesser effect on ionic strength and solvance effect. Before I show you the results, so how do we get these ligands on the surface? Well, in the same way as the ferrocene, so we do click chemistry on these looped aptamers, and the protein will actually interact with this bigger loop here on the aptamer and will guide the interactions. And you see again actually that the IV curves don't change when you even click aptamers and PEG units on it. So how does this now look for a sensor? Let's start off with the DNA gFET sensor. You can titrate these curves nicely. You can modulate to a Langmuir bloodshed isotherm. And from this, actually, you can get the KD values out. So KD values between CTNI and this aptamer is around 51 picogram per milliliter, corresponds to about 1 picomolar, which is quite nice affinity constant. And what's even more interesting, actually, if you interact it with a non-specific biomarker like BPM32, which is another cardiovascular sensor, instead of having an uprise signal, actually you get a decrease of the signal, which makes the sensor extremely specific, therefore. How would that now work on the PNA one? Well, to our big surprise, actually, we almost got similar results. We got a similar KD value. We got a similar limit of detection. So in the DNA, it was around 3 picogram per milliliter. On the PNA, it's 6. I mean, it's double, but it's still extremely good with the same linear range. So that would actually mean that in this type of aptamer, the charge seems not to have an effect on the final readout of this gFET effector. To eventually investigate if there is any point to using a PNR aptamer for gFET measurements, what we performed is we compared SPR measurements and gFET measurements in different ionic strengths and investigated the effect on the key value. So what you actually see is, if you look at the PNA, independent of the ionic strength, the KD is completely constant. While in the case of the DNA, depending on the ionic strength, this will actually change. In contrast, in SVR, you will have constant values all the time. That means, in general, the PNA value should be a much more stable and robust bioligand for overcoming charge effect or salt effects you will have in biological samples. So to finish off, I simply want to show you one more this graph. That means we really pushed it to the end. We finally got samples from 15 patients with different levels of CTNI, which we dosed in ELISA and then compared it to our gFET sensor. And as you see, actually, all these 15 samples we could identify into the right groups: low levels, elevated levels, and high levels of cardiotroponin. So with this, I hope I have shown you the interest of diazonium chemistry on these different sensors. I will not have time to talk about other chemistry and compare it to other devices. What I still can do is to thank all the people involved in it, especially the PhD students and postdoc, Teresa, Adrien, and Vlad, all the funders and collaborators on the project. And thank you on coping with this distance presentations, which was